Did you know there's differences in the energy stored in propane fuel versus gasoline fuel? And that using the chemical reaction, we're able to calculate the difference in energy. This lesson is on harvesting chemical energy. So, cellular respiration and combustion are similar because they both use organic compounds. One uses glucose, one uses fuel. They both use up oxygen and produce carbon dioxide and water vapor. And they're both exothermic, so they release energy. But they're different because the rate of respiration is slow and controlled by cells, while the rate of combustion is typically fast and controlled by the amount of oxygen in the environment. So, when we talk about the heat of combustion, this is the energy that's stored in the molecular bonds of different fuels. The amount of energy stored in a fuel is called the heat of formation. Now, this is in your data booklet on page 5, and the symbol is delta H naught F. So, the change in the heat of formation. Now, this chart will give you the heat of formation for some different fuels. Elements, because they don't have molecular bonds, their heats of formation are going to be 0 kilojoules per mole. They don't form. So oxygen, for example, which is going to be in every combustion reaction, has a 0 kilojoule per mole heat of formation because it doesn't contain those types of bonds. So during a reaction, typically we have an energy change. So chemical energy changes to kinetic energy in most reactions. During the combustion of octane, the chemical energy stored in octane is released, and the kinetic energy of that system is going to increase. So if we see that blue line as our reactants, we have a low kinetic energy, and as we progress through from reactants to products, we have a high amount of kinetic energy, and our potential energy drops. So this is the energy change we're going to see. So we can measure the heat of reaction using a bomb calorimeter. So this is a device used to measure the heat during the reaction. As we burn different reactants in a insulated chamber, then we calculate the change in the heat of the water around it. So because we know the specific heat capacity of water, we're able to calculate the amount of energy that was in those reactants due to the change of temperature in the water. So the heat of formation can also be calculated using a formula, and this is on page 5 of your data booklets. And the formula is the change in the heat of reaction is equal to the sum of the moles of the heat of formation of the products, subtracting the sum of the moles of the heat of formation of the reactants. So when we look at the moles, this is going to be the coefficient in a balanced equation. And like I said, on page 5 of your data booklet, you're given all the heats of formation. So the first thing you have to do to calculate the heat of a reaction is to ensure your chemical formula is balanced. So important to note that water liquid and water vapor have different values. And most of the combustion reactions in Science 30 are going to produce water vapor. So just double check that as you're going through your equations. So carbon dioxide and water vapor are the most common heats of formation used. And elements, so you won't find oxygen on this table. And so elements such as oxygen are going to have a heat of formation of 0 kilojoules per mole. So there we have water vapor at the bottom and carbon dioxide near the top. So when we're looking at a graph for a heat of combustion, an exothermic reaction is going to have a negative heat because energy is going to be released. Combustion reactions are exothermic, and we can see this in the graph below. So we have a hydrocarbon that was burned with oxygen because it released energy to the environment is now going to have a lower amount of potential energy, and there's our products of carbon dioxide and water vapor. So endothermic reactions have a positive heat because energy is absorbed. So the formation of benzene, for example, is endothermic, and heat is going to be formed. So to calculate the heat of combustion, first you want to write a balanced hydrocarbon combustion reaction. So this is going to be your hydrocarbon plus oxygen produces carbon dioxide plus water vapor. We want to organize the heat of formation for each product and each reactant in the table. And again, remembering that oxygen is going to be 0 kilojoules per mole. Multiply each heat of formation by the coefficient, which is the number in front of our hydrocarbon, oxygen, carbon dioxide, or water compound that make our reaction balanced. And then we're going to add all the product heats together and add all the reactant heats together. Then we're going to subtract the sum of the products minus the sum of the reactants. So what we're left with, subtracted what we started with. And then we're going to write down our answer with the desired units. So here's an example of the combustion of methane. So we start with a chart with our products and reactants. And then we have the heats of formation here in the chart. So step 1, have a balanced chemical reaction. So methane gas plus 2 oxygen gas produces carbon dioxide gas plus 2 water vapors. So as we go through, we're going to write down our heat of formation, products minus reactants. So we have 1 multiplied by negative 393.5 kilojoules per mole for carbon dioxide, plus 2 multiplied by negative 241.8 kilojoules per mole for water vapor. Subtract 1 multiplied by minus 74.6 kilojoules per mole for methane, plus 2 moles times 0 for oxygen. So we're going to multiply by the coefficients and then subtract our products from our reactants, and we get negative 802.5 kilojoules of energy produced in the combustion of 1 mole of methane. So when we look at the combustion of propane, we have our balanced equation. 1 mole of propane plus 5 moles of oxygen produces 3 moles of carbon dioxide plus 4 moles of water vapor. So in step 2, we have identified all the different heats of formation. So for propane, we have negative 103.8 kilojoules per mole, oxygen 0, carbon dioxide negative 393.5, and water negative 241.8. And you'll find you'll understand or just know what carbon dioxide and water are because you'll use them so often. Now we want to multiply our equation. I don't often cross out the, they're just crossing out the units there. So we want to multiply our coefficients by our heats of formation. And then we can subtract our reactants from our products. And you don't have to do this in more than one step. If you can just put it all into your calculator with appropriate brackets, your calculator will do all these steps in one. And then we have our final heat of formation of negative 243.9 kilojoules. And again, a negative number means an exothermic reaction and energy is given off to the environment. So like I said, you don't have to do multiple steps of calculations. If you can appropriately use brackets with your calculator, you can if you so desire. It's important to make sure that you're multiplying your heat of formation by the moles of each compound in your equation that is balanced.